Okay, so it's my great pleasure. It's my great pleasure to welcome Lola Ugarte to this DaSSWeb. Lola, thank you very much for accepting to be with us today. Lola is currently a full professor of statistics at the Department of Statistics, Computer Science and Mathematics at the Public University of Navarre, Pamplona. And her main research lines are spatial and spatio-temporal statistics and small area estimation. Her research group has made pioneering contributions in disease mapping by developing new spatial-temporal models. She has more than 100 papers published in international journals and has published or edited 13 books. She has delivered many seminars at well-known universities, such as British Columbia, Simon Fraser, Texas A&M, and so on. She has also been editor-in-chief of the journal Test, guest editor of several journals as Computational Statistics and Data Analysis, Environmetrics, Statistical Methods in Medical Research. She has been associate editor at the Journal of Royal Statistical Society, Series A. She has been chair of the statistics department at her university and coordinator of inter-university doctoral program in mathematics and statistics at the Public University of Navarre. I would like to mention that in 2021, she received a prestigious prize, CEU BBVA prize, for the contribution for the best applied contribution in statistics, given by an international jury for a paper studying crimes against women in India, and the paper was published in the Journal of Royal Statistical Society, Series A. But last but not the least, she is now the president of the Federation of European Statistical Societies. Lola, the floor is yours. Thank you very much for being with us.
Thank you, Maria Eduarda, for this kind introduction. I think you said too many things. I appreciate very much your invitation, and I'm very pleased to share my talk with people from Portugal and maybe from other places, but especially there. I don't know the audience. I really like to give presentations in person, but of course I understand that sometimes this is also a nice possibility. I'm seeing Giovanni there that he knows disease mapping, but there will be other people that perhaps not, and I didn't know. So my presentation is general in a sense, but some of the things that I will present at the beginning are simple things, let's say. It's an introduction to disease mapping a little bit for those people that don't know anything about, okay? So the outline of my talk is the following. So I will talk a little bit about what is disease mapping and why is it important. And then a very few words on historical notes on disease mapping. Then I will introduce to what is, in my view, most typical models, most typical spatiotemporal models for analyzing data in this area. And then I will move into multivariate models. I don't think I will have time to talk about high-dimensional data and other research topics, but we will see, okay? So I'll stop in 45, 50 minutes, I guess. Okay, so what is disease mapping and why is it important? I will define disease mapping as the collection of statistical tools to describe the spatial or the spatiotemporal distribution of a disease. This is what is mainly disease mapping, and there are two main goals. There might be other goals, but I see two main goals, which the first one is to unveil underlying spatial and spatiotemporal patterns of a disease, usually a non-transmissible disease, and also to detect high-risk areas or hotspots. We might be also interested in detecting low-risk areas, but mainly to detect high-risk areas. And why is this important? Because the information is of great interest, mainly for health researchers, epidemiologists, for them to formulate hypotheses about the disease etiology, or even to look for potential risk factors. And why is it important for policymakers? Because it might help to allocate economic resources efficiently, and then to implement new prevention or intervention programs, like many of these programs, screening programs, for example, in breast cancer or other type of cancers. Okay, so this field is of interest, and is one of the nicest applications in what is called lattice data in spatial statistics. So let's go a little bit about a little bit of history. Well, first, why it's important to look into areas or regions? Because usually individual factors are not enough for understanding the possible causes of a disease. And then it is important to consider contextual factors of the areas of residence, such as habits, diet, pollution, or other things that are mainly related to the region where the people lives. Hippocrates in the 4th century before Christ talked about these factors. For example, he thought that diseases occur as a consequence of such things as food, occupation, and especially climate. So where people live is also important. It affects their own health. Sorry. So probably, at least Giovanni knows that one of the most famous early medical map is probably this map, where these doctors know was able, he put some dots here, mapped cholera cases in London, and was able to determine the risk factor, which was a contaminated water pump on Broad Street. He was able to communicate this to the health authorities, and then they stopped using this water pump, and then it seems that the cholera cases decreased dramatically. So, of course, nowadays, we cannot represent just observed cases in a map, because populations need to be taken into account. We know from the pandemic times that perhaps sometimes people talk about number of cases per 1,000 inhabitants as one of interesting measures, but epidemiologists also use classical statistical measures to analyze incidence or mortality data, what is called the standardized mortality ratio, that we compute per each area. And it is simply defined as the observed number of cases divided by the number of cases we would expect to observe if that area had the same mortality rate as the whole region. For example, we might think in calculating a standardized mortality ratio in the different provinces of Spain, okay? And then we compute that for each province, and then we compute the expected number of cases using the global rate of Spain. And what is this SMR, in fact? In fact, it is simply the maximum likelihood estimator of the relative risks when we suppose or we assume that the number of observed cases, they are all independent and follows a Poisson distribution with mean EI times RI, where EI, this EI here is the expected number of cases that usually is treated as an offset in the model. So if we compute here a maximum likelihood estimator of RI, then we will see that this is simply the standardized mortality ratio. But these measures, what happens is that they are highly variable, mainly when analyzing rare diseases with few cases, or areas with very few population. And then they are so variable that we need, in a sense, to make them more reliable, to try to smooth these measures. And how do we smooth these measures? Using more sophisticated models like a hierarchical mixed Poisson model. We could use also hierarchical mixed binomial models or even negative binomial models, but usually the most used model are these hierarchical mixed Poisson models, which incorporate spatial dependence, temporal dependence, as well as spatiotemporal interactions. And what these models are is that they smooth the rates, and then they permit easy visualization of the underlying geographic pattern of the disease. For example, here, these are lung cancer mortality in Spain, and then we can see in the map of Spain, where are the high-risk areas? These red areas here, here, and here. And we can see also how this geographical pattern evolves along the years. Okay, so this is the information we could provide to epidemiologists. Together with the estimated risk, we could also give, of course, what is the probability that these risks are really significantly higher than 1, for example, okay? And this is the kind of information we give. But now let's introduce a little bit to the models that are behind these maps, okay? So I will introduce these space-time models very briefly. As I said, these models have been widely used to study these geographical and temporal patterns of incidence and mortality risk, particularly cancer, but also other non-transmissible diseases. Even they have been used for transmissible diseases, I don't think these are the best models for doing that. We also, or people, or at least our research group, we have also used this model to study spatiotemporal patterns of gender-based violence, mainly in India, and also to study geographical patterns of mental diseases. We have been the pleasure to collaborate with a very famous and good researcher, psychiatrist here in Pamplona. So as I said, these models then that will incorporate the spatial, temporal, as well as spatiotemporal interactions, we will reveal the global geographical patterns, the global temporal trends, as well as the specific region-specific temporal trends. So let me introduce now the models. I will introduce a little bit of notation. Suppose capital OIT and capital EIT are the observed and the expected cases of mortality of a disease in area I and time period T. And then, conditional on the relative risk, we might assume that the number of cases follows a Poisson distribution with this mean. Again, this EIT is the number of expected cases in area I at time T. Now we compute this taking into account the age groups in order to standardize by age, because the mortality is not the same in the different age groups. But then, so the log of mu is equal to this expression here, and now what we model is the log of the relative risk in this second hierarchy, and then depending on the specification of the log risk, different models, we can take different models. For example, we can specify the log risk of area I at time t as the sum of a global intercept plus a spatial random effect plus a temporal random effect plus a spatio-temporal random effect. And now let me introduce which are the distributions that we usually give to these terms here, okay? So I will talk about priors instead of distributions because I will be fitting the models in the Bayesian paradigm. But if you are frequentist, you might think on giving distributions to this random effect, you can be empirical based. One of the most famous priors for the spatial random effect is what is called the intrinsic prior, which is due to Besac. And the idea is the idea of introducing a spatial dependence of neighboring areas. And then the effect of the random effect in area I, given the rest of the areas, is assumed to be normally distributed. And then here, this is the weighted mean of the neighboring areas of region I. Okay, so we can give this weight, if they are equal to 1, then we consider that the random effect of area I, given the neighbors, is simply the mean of the neighbors. So we are kind of taking information from the neighboring areas. And then the variance is sigma squared divided by the sum of these weights. If we are using just adjacency, and if these weights are then equal to 1, then this will be equal to just the sum of the neighbors, okay? Okay, this conditional distribution, it can be seen that the joint distribution can be expressed as this, then the vector of random effects is multivariate normal with mean 0, and this is the covariance matrix. And then this Q is just what is called the neighboring matrix, and we are using here just contiguity, okay? Just we are going to say that two areas are neighbors if they share a common border. And then this matrix has simply in the diagonal matrix the number of neighbors, and the off-diagonal matrix are just -1 if area I and j are neighbors or 0 otherwise. This matrix is singular, and then if we need to compute the inverse, we need to compute the generalized inverse, and we usually use the Moore-Penrose generalized inverse, and there are reasons for that. I am not going to go into that. But apart from considering that there is a spatial dependence, we can also consider other distribution for the spatial random effects, like the Leroux-Carr prior, and then the structure matrix. Okay, the structure matrix, which for me is the precision matrix without the variance component, can be expressed like this. And then if you see this lambda parameter, which is a kind of spatial smoothing parameter, can take value between 0 and 1. Notice that if lambda is equal to 0, all the variability will be spatial, and if lambda is equal to 1, sorry, all the variability is spatial. If lambda is equal to 0, this neighboring matrix disappear, and all the variability will be unstructured. Okay, so there won't be a spatial structure variability, but they can be both. Okay, this is in my opinion perhaps a more appropriate prior for many of the diseases that we might study. Okay, but there are also other spatial random effects like the BIM2, one prior that we developed with Charmaine Dean in 2001. We published a paper in biometrics, etc. Okay, so which are the distributions that we give to the temporal random effects? We could give autoregressive distributions, but we usually use random walks for the temporal random effect, and then the conditional distribution can be expressed like here. In fact, to consider a random walk of order 1 is like an intrinsic car in time, but we all can also consider, because we have the neighbors in time, the t-1 and the t+1, or we can consider a random walk 2, which is not an intrinsic car anymore, but you take into account more neighbors, two previous neighbors in time and 2 posterior neighbors in time. And then the joint distribution can be expressed like this, and then this R gamma is the structure matrix of the spatial random effect. And then we have the spatiotemporal random effect. And then of course, we can consider other distributions, but usually people use a multivariate normal with 0 mean, and then the structure matrix can be of these different 4 types, which simply means if we consider the type 1 distribution, this Kronecker product of identity matrices, this means that all the random effects, the spatiotemporal random effects, are completely unstructured. They don't have a structure nor in space nor in time. If we consider type 2, we have some structure in time, nor a structure in space. Type 3 is the opposite. We don't have a structure in time, but we consider the random effect structure in space, or we can consider them a structure in space and time. To me, if I have to explain this, I might say that for type 4 interaction, the areas that are neighbors will have similar temporal trends. And these temporal trends will be temporally structured, okay? So this is, for example, what type 4 might mean. Okay, so as I said, as we'll follow here a Bayesian paradigm, we need to specify hyperprior distributions, and there can be many possibilities. Usually we consider a uniform 0,1 for the spatial parameter lambda in the Leroux prior, because this parameter moves between 0 and 1. And following some advice from a paper by Gelman and others, we consider uniform priors on the positive real line for the standard deviations. And sometimes we consider what is called nowadays penalized complexity priors for the precision parameters. In our experience, similar results to those obtained using uniform priors on standard deviations are obtained. Okay, so in principle, there are no many differences on using uniform priors or these PC priors, as I said. Okay, now just to have an idea, I would like to comment on some additional advantages and disadvantages of these models, in my opinion. Okay, so advantages: the models are very flexible to describe real situations, and I will give you some references now from our research group. And I think that model interpretation is simple and appealing. And I put an asterisk here because I will talk a little bit about this in a couple of slides. Which are the disadvantages of these models? If you need to program them by yourself, you have to take care because the models are not identifiable. There are identifiability problems with the intercept, which has to be with the singular, which has to be with the neighborhood matrix is singular, okay? And also the space-time interactions can be confounded with the main effect, okay? So talking about this model interpretation a little bit more, I have to say that, of course, when models are not identifiable, we can put different constraints, and then alternative space-time models can be used. So what I recommend, or we recommend, to compute what we call posterior patterns to ensure comparability and ease of interpretation of the different terms. So once you have fitted and you obtain the log of RIT, then we can compute these eta star, psi I star, which are the spatial patterns, temporal patterns, and the space-time patterns. And then it can be easily checked that the log risk can be decomposed at the sum of these patterns. So, for example, if instead of using the models that I introduced, you use splines, for example, you could compute these posterior patterns, and that's nice because you can compare the different terms using different models. And since these patterns are centered at 0, we are able to decompose the total amount of variability of the overall loss risk as the sum of the spatial, temporal, and spatiotemporal variabilities, and then it would be possible to compute the percentage of spatial, temporal, and spatiotemporal variability using this. So that's nice, okay? Well, I can give you some references on model identifiability using constraints. We wrote the paper together with Jim Hodge from University of Minnesota, where we completely specified the identifiability constraints, and we saw how this might affect frequentist inference as well as Bayesian inference. And this is what we do in this paper that, by the way, has quite a few citations because it's fairly clear. You want to write, for those of you that don't have any experience about the spatiotemporal modeling, you might want to have a look to this nice paper. This is the paper where we received the prize. It's called Crime Against Women in India, Unveiling Spatial Patterns and Temporal Trends of Dowry Deaths in the Districts of Uttar Pradesh. And this is a very nice paper where we comment on the different priors, and then this is a very well analyzed kind of data. Is very nice. And if you want to deep on computing posterior patterns, you may want to read this paper that we wrote together with Martinez Benedito and Botella Rocamora, people of my group. Okay, so now I will present some real data, but it will be in this part of my talk. Okay, in the part where I'm going to talk about multivariate disease mapping. Okay, so as you might know, the univariate modeling of several responses is very informative. But of course, if we are able to model jointly several diseases or several crimes, this could improve precision estimates, but also allows for computing correlations between the different crimes or between the different diseases. And we think that this is particularly relevant when we do research of crimes against women, which is a very complex problem where the factors that might be related to the phenomenon are unclear. So as I said, this multivariate modeling allows us to provide correlations between the spatial and the temporal patterns of the crimes that may reflect the association with common underlying risk factors and also the connections between the different forms of violence against women. What happened with this multivariate modeling? That the use in practice is still limited because the implementation of these models is not easy at all. It's fairly complicated. Just for giving you an idea, most of the research extends univariate conditional autoregressive models to the multivariate setting. And one of the pioneering was the work by Maria in 1988. In 2018, when I was the editor of TEST, I invited Jean McNabb to write a review on the construction of multivariate proposals. This is a very nice paper, perhaps a little bit theoretical. And there are like 3 approaches to build different multivariate proposals. But an appealing approach is what is called the co-regionalization framework. And if you are interested in this, I will recommend a paper which was published in Biometrica in 2013 by Martinez Benedito, where he derives a general co-regionalization framework, but as he was able to say, this framework was computationally intensive. And then 2 years later, together with Botella Rocamora and also Sudipto Banerjee, they proposed what they call M models to reduce computing burden. And this is also a very nice paper. We our group, we use these M models, we extend them to the spatiotemporal context, and we analyze 2 forms of crimes against women in the Indian state of Uttar Pradesh in India. Now, of course, when the observed risk variability within responses, within crimes or within diseases is high, we could also use splines for smoothing risk. And we think that this is an attractive modeling approach. We already published some papers on this in 2010, a pioneering paper on using penalized splines in disease mapping. But the research on multivariate spline models for spatiotemporal array delta is not so abundant, but it mainly focuses on multivariate structures to deal with the spatial and temporal dependence for one response measured in several time periods. And then in this case, the structure matrices of space and time are known, and only the precision parameters controlling the degree of smoothing have to be estimated. So we, in our recent paper, what we do is we introduce a real multivariate p-spline models for spatiotemporal data, but with multiple responses. This is the model that I'm going to introduce now, and then I will present to you a case study, okay? So the model description is as follows. Now we have 3 indexes, one for the area I, time t, and then jth is the response, the crime. So we have jth responses, jth diseases, jth crimes, jth whatever you are studying. Okay, now conditional on the relative risk, we again assume that the number of cases are Poisson distributed. We again have the expected number of cases that we will treat as an offset in the model. So as if they were known, and then now the log risk, we model it in this way. We consider an intercept for the J response, a smooth spatial surface that we are going to consider that it will be well estimated using penalized spline, where here x1i and x2i are the longitude and latitude of the centroid of the area, then a smooth temporal trend. So instead of considering here as before a spatial and temporal effect, we consider this spatial function and temporal function. And then we also consider a spatio-temporal interaction random effect for each of the responses. And because we consider this a kind of a residual term, we do not consider any surface or any function here to model this space-time interaction for each response. Now, how we model this smooth spatial surface? We consider it can be expressed as the product of a 2-dimensional B-spline basis time the vector of coefficients for the J response. And this B-spline basis for the space is just the row-wise Kronecker product of the marginal basis for longitude and latitude. This basis was introduced in a paper by Ehlers and others in 2006. And now, to achieve a smoothness and not to have a very wiggly surface, what we do is we assign a prior distribution with a Gaussian kernel for the vector of coefficients. And here, P is the precision matrix, and it's expressed as the linear combination, this linear combination. Here, lambda 1 and lambda 2 control the amount of smoothness in longitude and latitude. And these P1 and P2 are simply the product of these different matrices. In fact, this is the Bayesian analog to put in some penalty on the coefficients as Ehlers and Mars did a few years ago. So this will be the Bayesian analog. So in fact, these P1 and P2 are the structure matrices of random walks of order 1 or 2, depending on the order of the different matrices, okay? So how do we model the smooth temporal term for the J response? In a similar manner, we use a temporal B-spline basis times a vector of coefficients. Again, we use the Gaussian kernel for the distribution of the vector of coefficients. And this time, the precision matrix is the product of P3, the lambda 3, and then these difference matrices. Again, this product will be the structure matrices of a random walk of order 1 or 2. What we do with the spatial-temporal interaction random effect? We assume a kind of Carr prior distribution. And now we consider the precision matrix, this M, where we might introduce type 1, type 2, type 3, or type 4 interactions, okay, as I explained before. And notice that I'm using a different precision parameter for each response. Now, QI is the spatial neighborhood matrix here, and QT is the structure matrix of a random walk of first and second order. But then I want to take account of the potential relationship between crimes. So I introduce correlations among the P-splines coefficients. How? I define a variance-covariance matrix of the spatial P-spline coefficients. So the coefficients of the J response and the covariance between, the covariance between the coefficients of the J response and the coefficients of the K response, and also for the temporal P-spline coefficients. So the diagonal terms will be this sigma squared, but the off-diagonal terms I express as the product of the correlation coefficients times the standard deviations. And I do this for the covariance matrix for the spatial P-spline coefficients, and also for the covariance matrix for the temporal P-spline coefficients. I also put the off-diagonal terms in terms of these correlation coefficients times the standard deviation. And I do not consider correlation between the interaction terms, because as I said, I consider the space-time interaction for each response as kind of residual terms, and it will complicate the model very much. Okay, so in order to introduce all these correlations into the model, what I do is I stack the risk for each disease, the one after the other, and I do the same for the different coefficients. Okay, so I can write the multivariate P-spline model in this complicated way. Okay, but then the prior distributions now will be this. Notice that now the precision matrix is the Kronecker product of the precision matrix to take account of the correlations between the different responses, and also to achieve smoothness. Okay, and also this is for the space, for the time, and for the space-time interaction. Okay, so what happened with these models? They are fairly complex. Okay, and there are some identifiability issues again. So we need to center the smooth functions to make them orthogonal to the intercept. We also need to take account that the interaction effects overlap with the main spatial and temporal P-splines, and then additional constraints are required. Also, if you see lambda 3, the smoothing parameter for time is not identifiable, because it can be subsumed in the covariance matrix or in the precision matrix, as you can see here. I have here a lambda 3. I can move the lambda 3 here in this product. Okay, so this lambda 3 is not identifiable. And only the ratio between lambda 1 and lambda 2 is identifiable. Lambda 2 can be subsumed into this matrix as well. So without loss of generality, we can set these parameters lambda 2 and lambda 3 equal to 1. But the good thing is that the correlation parameters are identifiable. So we will be able to talk about correlations between the different responses. So how we can fit this model? Well, we use INLA to fit these models. However, the problem is that these new models were not available in our INLA. So we needed to implement the whole thing using what is called the R generic constructions. So we did this very carefully, and you can find details in the paper, and we also have the code available in the GitHub of our research group. I will not go into details. It's complicated. If you want to see, you can go there, okay? And now, what I'm going to do is, I'm going to illustrate this fairly complicated model to analyze crimes against women in Maharashtra, in India, okay? As you know, violence against women is a very complex and terrible problem, mainly in countries like India and also in other countries in Africa. But of course, in our Occidental countries, it's also a problem, but here the problem is terrible, no? Is a problem, as the World Health Organization declared, is a problem of epidemic proportions. For example, in 2021, the World Health Organization estimates that the global prevalence of physical or sexual intimate partner violence among all EVA partner women aged 15-49, between 8 years old and 49 years old, was 27%, with this range between 23 and 31. So it's a really terrible problem. Okay, of course, in many countries, the patriarchal nature of the state produces this gender inequality, which in turn contributes to increasing violence against women. And India, as I said, is a paradigmatic case. We all remember all these problems in public buses. Last year in Spain, a couple was terribly attacked, and a woman even was with the husband in India. It suffered terrible sexual abuses, no? So here I will focus on 4 crimes against women in the Indian state of Maharashtra. I will show you where Maharashtra is in the map of India. And I will focus on 4 different crimes: rape, assault or criminal force to women with intent to outrage her modesty, cruelty by husband or relative of husband, and kidnapping, okay? I will call like this. For precise definitions, you can go to the Indian Penal Code. You have here the map of India, and you have here the state of Maharashtra. Maharashtra, for example, is the state where Bombay is located, okay? Just to have an idea. We analyzed data for the 34 districts of the state over this period, 2001-2013. Just to have an idea, this is the 3rd largest state in India. Is of the size, for example, of Poland or Italy. Is the 2nd most populated Indian state, and we are dealing of about 29 million females between this age, okay? Because we consider between 15 and 49 years old. And just to have an idea, male literacy rate is 88%, is about 6 points higher than the Indian male literacy rate. Female literacy rate is a little bit lower, 75, which is about 10 percentage points higher than the Indian female literacy rate. You have here some summary statistics of the 4 crimes over the period. We compute coefficients of variation, and there is quite a high variability between the figures. And here, what I represent, this is what I call the how it's called circular plot. And then I represent here all the states And we see that there is a huge variability of Q rate per 1,000 women, okay? So we are seeing here that it seems the cruelty, assault, rape, and kidnapping in that order are the most, the biggest rates of crimes here, no? I see here, in general, as I said here, the lowest rates of crimes correspond to the most western districts with the exception of Greater Bombay, okay? So I give here a few details about how we fitted the models. We use cubic B-splines with first and second order random walk prior for the spatial and temporal coefficients. Here, the internal number of nodes, perhaps it's not too important now. What we did at the beginning to analyze this data is we feed univariate models to each crime with the 4 types of space-time interactions. And then all the model selection criteria that we use the deviance information criteria, we use the Wakaike information criteria, we use the log score. All of the univariate models point towards type 2 interaction. So it seems that the space-time interaction is a structure in time, but not in space. So we decided to consider these type 2 interactions for the multivariate models, okay? Then we consider also some hyperprior distribution. For the covariance matrices, we use Wishart distributions, again, for 1 over the square root of lambda 1 uniforms, and also for the standard deviations. And how to implement these priors in INLA is not trivial at all. It takes a while, okay? So it's not easy. So we fitted many models. Here I'm showing you some of the models that we fitted. We fitted, of course, as I said, type 2 interaction for the space-time interaction for each crimes. We consider temporal correlations and absence of temporal correlations, and we use different ordered penalties for the spatial and the temporal component. And here, as you see, the best candidate is a model accounting for correlation between the coefficients of the spatial and temporal B-splines. Or I use the structure matrix for the Gaussian prior of the coefficients. I use a random walk structure matrix, random walk prior, and also for the same for space and for time. Okay, it was better than the random walk 2. So which are the results? Here, I'm representing the posterior median of the district-specific spatial risk for each crime. In other words, this is the geographical pattern of the different crimes, okay? Here we have rapes. We have higher risk with when the colors are more intense, the red colors are more intense. So we see that the geographical pattern of rape, assault, and kidnapping are fairly similar, and cruelty is a little bit different. And it's interesting that this rape, assault, and kidnapping are somehow sexual related crimes. Cruelty is a crime against women, but maybe is a little bit different. So the highest correlations that we have is with that we find is between rape and assault. You see here the high correlation. Also between rape and kidnapping, and between assault and kidnapping. This is on the verge of statistical significance, and cruelty and kidnapping, you don't have any spatial correlation. And here we have the temporal patterns, the global temporal patterns of incident risk for the 4 crimes. And again, rape and assault are the most similar. Also assault and kidnapping, and cruelty behaves a little bit with this wave shape similar to assault, but in principle, very different, okay? And here I decided to choose four different districts, one called Aurangabad, Gadchiroli, and Greater Bombay, and we see that the risk evolution for these 3 selected districts is very different. For example, Aurangabad in cruelty has a relative risk which is almost double the risk in the whole of Maharashtra, and statistically significant. And we see here that assault is a little bit different, rape is very low, And Garchiroli, you see that very, very different behavior compared to Aurangabad or Grita Bombay, where we have high risk and they are very increasing in the last year in rape, assault, of kidnapping, and cruelty was below the risk of the whole region. And what we also did is to use functional bus plots to see if we could find any outlying district. And then we use the final relative risk that we estimate to use and use this functional bus plot used by Sun and Ganton. And we found Warda as a district that was a kind of outlying district in rape and assault in certain years, okay? It seems that the rest of the district, we couldn't find any outlying district, okay? So let me make some final comments on our proposal. So what we did in this second part of my talk is we propose multivariate p-splines to broaden the class of multivariate models. And as you see, they allow to account for spatial and temporal correlation between crimes. We were able to implement the models in ELA using the R-genetic constructions. We were also able to see that estimates are more precise than those obtained using univariate models. And even though there were some identifiability issues, we centered the smooth functions and the correlation parameters, we could identify them properly. So, and that was good. We also analyzed the sensitivity to the number of nodes. We saw that increasing the number of nodes in longitude and latitude beyond 10 increases computing time, but that did not reduce model selection criteria, and the estimated spatial patterns did not change. However, using more than 5 internal nodes in time seems to overfit a little bit. So in general, the correlation between the spatial patterns don't change too much, but we found some differences in the posterior correlations between between the temporal trends. And regarding the real study in Maharashtra, we think that results are very interesting. We saw similarities between the spatial patterns of rape, assault, and kidnapping, as I said, sexually related kind of crimes, with a kind of northeast-southwest gradient, whereas the spatial pattern for cruelty is a little bit different, with a northwest-southeast gradient. With respect to temporal evolutions, the greatest similarity were those of rape and assault. We were also able to identify districts with high risk for some of all crimes examined here. And we use functional bus plots as a tool for finding some outlying district with regard to the risk of rape and assault that we found this Warda in the northeast corner of Maharashtra. Which are the potential limitations of our model? We wrote in the paper that the potential limitation is the number of hyperparameters increases with the number of diseases. But I have to say that nowadays this is not such a big problem, because with the new fitting strategy in ILA, the compact strategy using variational base, the number of hyperparameters is no longer a problem. But the limitation, which is really a limitation concerning the real case study, is that there may be, surely there may be some underreporting of the number of cases because of the social stigma when you go to report this type of crimes. So this might be a problem. And we saw a big increase in the last year of the study. And this might be because of the change of government and so on, that where you can find these things, okay? So you can find details in this paper in biostatistics, which is called Multivariate Bayesian Spatiotemporal p-spline to analyze crimes against women. And you have also the code to feed the model in our GitHub, in the GitHub of our research group. I'm going to finish here because I don't want to be too long. Just let me introduce you to my research group. This is the Spatial Statistics Group at Public University of Navarre. And the work that I presented today is mainly due to Tomás and Aritz and Jayone and Gonzalo, which is from Argentina. He's now there. And there will be others that are also contributing, but perhaps not in the particular things that I presented here. In the high dimensional part is Eric Orozco, but I didn't present that part here. So just to say that this work has been also supported by projects of the Spanish Research Agency. And thank you very much for your attention. I'm sorry that I cannot see your faces, okay? But that's okay, to interact a little bit more. Thank you.